Log on, tune in, find out. Another good idea from Cambridge.
Yeah, ready. Okay.
Okay, good morning. So we start the first lecture with Dora with PIP.
All right, thank you. So I was in the other building and wondering where everyone else was. And of course, the correct question was not where everyone else was, but where I should be. So I'm glad this all worked out. All right, so we're in the last lecture. We've discussed a number of things I want to summarize, for particularly for the students, and then say some newish things. So this lecture is sort of on variations and applications. But to sum up, quickly, when G is reductive, and the characteristic of the field is 0, just for convenience, we discussed X being affine. We have our natural map of invariance, which is just the map to spec the ring of invariance. And when X is projective, we have now a map of some which restricts to some open subset. So it's a rational map there. Here it's an actual morphism going to, so we'll do it this way, X semi-stable / G, which is then projective variety. So this is proj K X G. Often by Bucer notation, we call this X / G. And of course, as I said, this is projective. And the basic idea was that we can reduce to studying linear representations, at least if this is a normal variety in the projective case, by simply considering a J-covariant embedding and using some functoriality. So you could embed J-covariantly into a projective linear representation. And for that, you might need X as normal to guarantee the existence of such an embedding. Then we have a stratification of sorts of our projective space with respect to this group action into the stable set, or if you prefer, properly stable set, which is open inside, potentially null, inside the semi-stable set, inside Pn itself. And the difference between each of these things will have special names. We'll call the difference the complement of the stable set and the semi-stable set the strictly semi-stable set, and the complement of the semi-stable set in the full projective space, the unstable set. Again, unfortunate notation. It should be the unsemi-stable set or something like that, but we'll call it unstable. And as a side remark to clarify some confusion some students had on the tutorial on Friday, there's this issue of closed orbits we were discussing. So as I was discussing these closed orbits in the context of the affine cone up above, or in the later Mumford definition we gave, the more general definition for GIT, constructing stable sets and so on in terms of these affine patches. But the issue of closed orbits was, as I said, in the affine cone, not in the projective variety itself. So we'll give an example, affine cone, or equivalently in the affine patch. So for instance, we had the example lambda 0, 0, lambda inverse acting on P1, and here we have two fixed points for the action, which are of course closed. The orbit of x is, if we pick a point x here, the orbit of x under this GM action is not closed in P1, and yet nonetheless it's stable. And the reason it's stable is that yes, it's the orbit is closed in, if you pick a representative x hat, orbit of a representative x hat is closed in the cone. Or if you prefer to think of it in terms of the Mumford definition, the orbit of x is closed in P1 minus, we need an invariant function. Invariant function, if these coordinates are x and y, just take x times y. So minus the set where xy is equal to 0. And then you see we've removed exactly the north and south pole, and now certainly the orbit, which is all of what remains, is closed, and all of what remains. So one other comment about this, note that even if we're talking about line bundles in the Mumford definition. This is degree 2. There does not exist a degree 1 invariant for this, so you sometimes have to take tensor powers of your given line bundle, perhaps, for your, of course, in order to get higher degree homogeneous functions. Okay, so that's part of a general observation that stability is independent of certain choices. And one of those things was that, so once you've picked your embedding into this Pn, you might want to embed into some much larger Pn again, via Veronese type thing. And this part here just corresponds, of course, to picking a different tensor power of the line bundle. So it's independent of L versus this around. Okay. Right. So then, as I said, functoriality, slide number, implied that we inherited the stratification. From Pn, just by restriction, by intersection. And furthermore, that means that in particular, stability analysis is just a feature of studying linear representations. And we saw even more, it's not just a feature of linear representations, it's really a feature of multiplicative groups. So we had the Hilbert-Mumford numerical criterion, which is, as I said, basically a statement about multiplicative groups. So if let's x be the representative of x in the affine cone, then we'll say that x is unstable if and only if there's going to exist some multiplicative subgroup such that the closure of the orbit contains 0. All right, and then you can interpret this in terms of the weights of the representation very cleanly and combinatorially. So would say that theorem, like sort of the numerical version of this, is that if x and x is given by homogeneous coordinates, x0 through xn, in Pn, we say it's semi-stable, respectively stable, for the action of a maximal torus, a fixed maximal torus acting diagonally on Pn with weights alpha naught through alpha n, if and only if the convex hull so convex hull of the alpha i's associated to the non-zero coordinates contains 0. So this is a statement about polytopes and where 0 sits relative to the polytope. Right? And remember this is the condition. And respectively, so that's semi-stable, respectively contains 0 in its interior. Right? And in particular, you can identify, so in practice, in particular, the way that you can identify stable points and so on is just you begin by identifying unstable points with respect to some maximal torus, and then you sweep out by your g action. Well, let's say sweep out by g action. So you take the union over all the g orbits of those. And the complement is semi-stable, and so on. Okay, so it's actually quite pretty. And not only is it pretty, but as I said last time, it has then a nice refinement. Whoops. That you can somehow pick out the most important multiplicative subgroups for the purposes of stratifying your unstable set further. And so this refines the stratification. In essence, by taking closest points to the origin on the polytopes associated with the unstable set, to origin on polytopes that don't contain 0. I'll give you a bunch of subgroups. And the basic picture, once again, is might have something like this: lambda squared, a lambda inverse with zeros, and then the weight you have, well, this is a weight 2, this is a weight 1, this is a weight -1, and there is 0. And so here, for instance, is a pair of weights corresponding to this and this, and the closest point is there. It doesn't contain the origin. It corresponds to something in the unstable set. In particular, in this case, it corresponds to AB0, which is just a copy of P1. Right? And so somehow, it's kind of one distinguished point and then an A1. So this decomposes, as I said, the point A1. The A1 itself you could think of as sitting over a point. So this is nice. In particular, if you are careful with this, then it gives you one of the main tools in working with cohomology of moduli spaces. Sort of now classical techniques, I guess, cohomological application. If you want to pass the moduli space, it's, in this context, the quotient, we can think of this Atiyah-Bott idea of equivariant perfection. So it tells us that if we look at our x and we think of x as decomposing into this semi-stable set, union over some strata, these unstable strata, we'll just call them SI. Yeah, it's just union of SI over I. Then you have a decomposition of the equivariant cohomology into this direct sum of equivariant cohomologies of each stratum, shifted by their codimension, so everything makes sense. And then, of course, you also need your zeroth stratum in the semi-stable set. And what's nice about that is if you're in the good context where the quotient by G of X semi-stable is not just a categorical quotient, but also geometric, so it gives you variety without any further collapsings with that second quotient stage, then we know that, so we'll say stable. Let's say X semi-stable equals stable. Simplest case. Then we know that this turns out to be isomorphic to the cohomology of this. All right. And so this we should think of as being our moduli space. And we want to, then you can apply it, of course, to, and was immediately applied by Francis Cohen and others, to moduli of the two classical examples, vector bundles and varieties. Vector bundles on a curve, so, and hypersurfaces of degree D. In Pn. So these are our basic models for moduli spaces arising as quotients. Come back again and again in many contexts, as people have seen this conference already many times. Get back to each of them in a more complicated setting in a moment. So, right. So a side remark about this is that as far as the stability analysis is concerned, singularities don't matter. They don't complicate the GIT. Don't complicate GIT. But they do complicate this sort of cohomological analysis. So you'll typically want lots of smoothness assumptions in place, or something which is close to amounting to a smoothness assumption, or replacing something singular with something smooth. So they do affect dramatically the cohomology results. Okay, so The next thing we said was that Mumford had extended the theory by patching these affines and picking G-linearizations. We're going to patch affine quotients together. And B, you can pick a G-linearization, i.e. a twist, by a character of G. Now, classically, on the affine patch, such a G-linearization was pretty standard. I mean, this wasn't something new in that sense. This is just revisiting old 19th century ideas in a way. So classically, this is called semi-invariance. Classically, on an affine patch, instead of looking at invariance, we're looking at semi-invariance. But it does lead to lots of nice geometric behavior when you take into account. And so as I mentioned last time, again, there's two crucial toy models. A lot of pairings in this thing. You sort of have vector bundles versus hypersurfaces. And here we're going to have sort of two things you can do. You can either do the ample bundles, lots of ample bundles, or vary by lots of characters. So the first, as I mentioned, was to a model that still gives surprising results when people look at it. Moduli of points on P1. And what you want to do is just vary the ample line bundles. So look at the ample cone, G ample cone. Said this links with many other problems in algebraic geometry, other moduli problems, problems about locally symmetric spaces. Surfaces, etc. Also links up with theory of locally symmetric spaces nicely. Hyperbolic structures, so on. Second, I mentioned toric varieties. And in that case, it's really taking this twisting by characters approach. The simplest thing possible is X is an affine variety. Act on it with a torus, and you're going to have your unstable set. It's just a union of coordinate linear subspaces. And the combinatorics is governed by the polytopes in the way you want, and you get a toric variety as a quotient. Okay, so again, it's sort of this theory of semi-invariance. Now, more generally than that, and sort of in keeping with this philosophy that somehow what we're doing is looking at multiplicative groups and their implications in algebraic geometry, you could try and link it up with Mori theory, as Keel and Hu did. You have Keel and Hu's Mori dream spaces. And the idea here is quite similar, actually, and it ties in nicely with finite generation as well. It's that, so here you could think of the quotient. The quotient is giving you your toric variety. Or you can think of beginning with a toric variety and looking at the torus bundle on the toric variety and taking its closure to fill in the unstable points. So if my toric variety is y, the other perspectives I could have begun with y, taken my torus bundle, it's called a B. This is going to be something quasi-affine. And if it's a finitely generated ring of functions, then you can take its canonical closure, go spec, right? And that should be codimension 2. And in this case, it turns out to be an affine space. The question is, where do we get this torus, this choice of torus vibration? And that just comes from taking all of your basically running through, so you have a finitely generated Picard group, and you're just taking the Cartier dual Picard group effectively for the fiber. So you're just summing over all the line bundles coming from a generating set, and that's sufficient. So this is the same idea in general here. Keel, Hu, Mori dream spaces. We're going to begin with something down below, which is thought of as, so we have X, y down below. We're going to have a few assumptions in place, like you want to have a finitely generated Picard group. You're going to take an associated torus bundle, and in the case where the associated torus bundle has a finitely generated ring of invariance, if K Fg, okay, this is still going to be quasi-affine, then just take the closure, embed this in spec KB, And now you have a beautiful picture with a torus action, a GIT quotient to y, and a nice understanding both of the G-ample cone and of a sort of Morey chamber decomposition. So the idea here is that Morey chamber decomp can be identified with the GIT chambers. They're thinking of them very explicitly. So it's again a nice toy to play with. And once again, you sort of, as I said before, we have this changing, this wall crossing. As you change from one chamber to another, there's a birational transformation, a sort of flip going on. So we'll see this in more detail in a second. All right, so remark. One remark is that there's lots of combinatorial control in these examples. But it's also a good way to get at something a little more, perhaps what you might think of as a little more exotic. Good to get at what you might call highly rationally connected spaces. All right. So rationally connected, makes sense for what that means. You're connected by chains of P1s, any pair of points. But sort of by highly rationally connected, well, there's another way of thinking of things. It's a little stronger. And that's that if you have a space like affine space, it's completely contractible. And an analogous way of saying this in algebra geometric terms is it's not just contractible topological space, but somehow in sort of formal A1 algebraic topological sense, all of the homotopy, A1 homotopy groups vanish. And if you remove from something which is highly connected, so all the low degree homotopy groups vanish, something of very high codimension, like say a point, then that doesn't affect the higher, it doesn't affect the lower pi i's. So for instance, if I'm in a 3 space and I remove a point, and I think contracting loops, I can still contract my loop. Right? But I do have a problem if I try and contract my sphere. But in 10-dimensional space, removing a point, I can contract many things. So, yeah.
Are you supposed to remove anything you want, or only things that built out of themselves, built out of A1?
So you can remove anything you like. It doesn't have to actually be built out of A1, but you do want to be a little bit careful. There's always technicalities. So you want to check that once you've removed something, the result is A1 connected. So you want to make sure, and then you can begin doing analysis. So you have to check that once you've removed something, you can still connect points by chains of A1s in a suitable sense. No, that will follow from a theorem that I proved with someone else. So it's but with a Schall. So the point is that with a couple technical conditions in place, then you can suddenly produce lots of things where lots of the where all the low pi's vanish, high pi's don't, and furthermore you have a sort of functoriality. So there's another bit of philosophy, if you like, but is that free torus actions. I mean, this is a theorem, but it leads to a philosophy. Free torus actions are in the A1 homotopy category covering spaces. So somehow all these nice GM actions we've been dealing with, at least if we throw away the singular loci, we basically have covering spaces. And so we've sort of been thinking of the theory of covering spaces in different contexts. So this, we have a long exact homotopy sequence for fibrations. What that means is that when you pass to the quotient by the torus, right? This, again, you're thinking of it as a covering space. So all the higher pi i's are going to descend and be the same above and below. So now on our toric variety or more dream spaces of various sorts, you're going to be able to say something about their higher connectivity properties. Right? And if you are curious, yes, it is the case that pi naught A1 for something smooth and projective being 0 is going to imply you're rationally connected. And the reverse direction would be true if you assume a different Grothendieck topology than the usual one, but whatever. The point is, this is at least as strong as rationally connected. So, okay. So, another remark is that the extra flexibility in the choice of our pair X and L is useful. In many contexts, we discussed you don't just have to consider L ample. Certainly, this doesn't have to be quasi-projective anymore, and this needn't be ample. But, as I said, the quotient is always going to be the quotient of your open subset by construction will always inherit a line bundle and be quasi-projective. Okay, so some examples of why this extra flexibility might arise naturally, or where it might be important in certain cases. It was asked last time if I could say something about it, so here's one quick thing. So for instance, you might have non-separated phenomena for X arising naturally before you quotient. So why? Well, here's one thing. Let's say we actually have a group that isn't necessarily reductive. Maybe it's reductive, and it of course has a unipotent radical. So this is going to be the normal subgroup. You might quotient by it first. So we might have X being some Y quotiented by U. It could be a perfectly nice free action, set theoretically free action, say, but it may be non-separated. And we saw this last time, maybe 2 times ago. For instance, I discussed the two-dimensional affine quadric with a group action, which gave you this non-separated, so single line with a doubled point. Okay, and on this, you still may have an R action. Have your reductive R action. All right, so there's an example of something which is not quasi-projective, but you're going to care. I mean, you wouldn't want to do it with just the line, but some higher dimensional example. Another one would be X itself may not be complete, and natural completions may not have, even if X itself has an ample line bundle, there's no reason for natural completions to carry a natural ample line bundle you'd want to work with. All right, so maybe X not complete. L over X ample, the extension not. A natural extension to some complete X bar. Another thing that can happen is you could be working with a group acting on X, and X might have an ample line bundle, and then you have to pass to a larger group and a larger space, sweep out by this G action, compatible with the H action, and then this will have some line bundle on it. No reason to believe that that's going to be nice in general, but you probably, if you begin with line bundle here, it's something canonical to do there. Another example, as I said, is oftentimes ample bundles aren't the things to consider. Naturally your problem, but semi-ample bundles are. And you still get your, with semi-ample bundles, take some tensor power, you get that it's base point free, and so you still have a nice rational map with projecting images and so on if you start with some projective. So I mentioned this 2010 Invenciones paper of Serre on the branching problem extending the Knudsen-Tau results on the Horn conjecture. And he does have to go through then a sort of G semi-ample cone analysis instead of just G ample cones. Okay, so that answers that question someone asked. So what if we don't have a G action? Well, GIT ideas are still useful. For instance, we sort of had a hint of it here already. Here we began with a G action to get something down below, but what the other perspective was begin with this, build a torus vibration, and you have a torus action there. So you could do something similar much more generally. What if you don't have a G action? Well, you can think of X as being the quotient, and then build a larger space. We'll need all these tools by the end of today. So this philosophy turned out to be very handy for birational geometry. So the motivating example is this so-called Tia flip. So let's call this L plus M. And we can consider then the action of GM given by t times x1 with t times x, I guess I called it L, and then t inverse times y1, t inverse times ym. Okay, and then the idea is that this makes sense. Of course, it's a multiplicative group action on something affine. We can get just take the ring of invariance. So this makes sense. It's a categorical quotient. And it's just the affine cone over a Segre embedding of a product of projective spaces. And we also can take two other quotients. We can consider, excuse me, this. We can consider this, where we subtract the loci where all this doesn't contribute anything, so all these are 0, and subtract loci where all these are 0. And then you take the corresponding quotients, and those turn to be geometric quotients. Right? And you get a flip between them, which replaces a copy of PL minus 1 with going there to a copy of PM minus 1. And here, assuming L and M are greater than or equal to 2. And so this sort of basic picture, sort of wall crossing, as I said before, is sort of the key ingredient for this theory of birational cobordism that then led to the proof of weak factorization. Yeah. Yeah. So this, I have an affine space, I have a multiplicative group action. The first L coordinates I'm going to multiply just by t to the first. And the last M coordinates multiply by t to the negative 1. Right? And if you can certainly just take directly the ring of invariance and spec of it, and that turns out to be, if you like, it's an affine cone over a Segre embedding. So this is a affine cone over a Segre embedding of the product of two projective spaces, namely PL minus 1 and PM minus 1. P. All right. And then what happens is there's an open subset here, two different possible open subsets. We can call them B minus and B plus. And they will each have geometric quotients. All right? And those open subsets are going to correspond to the complement of the vanishing locus for the y's or for the x's, respectively. Okay? And then there's a natural flip going from this to this, which simply is replacing PL minus 1 with PM minus 1. Okay, so you're describing a birational map by somehow passing to a larger space, a one-dimension larger space, with a GM action. And then just taking this variation of GIT quotient. Okay? So that's the idea. And then you can try and do this iteratively. You can try and zigzag. Right, so you'll have some x1, and you'll have a y1, and you'll have an x2, and a y2, and so on. Right, and your hope would be that if you adapt things appropriately, you might eventually be able to factorize a birational map into some sequence of things like this. And that's the basic idea. Of course, in practice, it's a bit more complicated, but the idea is there. And with locally étale, everything works OK. So this, though, led to, as I said, I won't pronounce his name properly, but Ledardic's theory of birational cobordism, where the rough idea, why birational cobordism? Well, we've passed this space up above here, and this space you can think of as having, there's these two different opens. We'll think of these quotients as somehow being the two different cobordant pieces. And it's birational because there's an open subset in which the two open subsets agree up above. Right? So it's, and hence down below there's an open subset they agree on. So it's not the best name given the current theory of algebraic Bortism, but it predates it. So, okay, and so then this idea was crucial in the proof of weak factorization, which, to remind young people, is the statement that if you have a birational map, say over a characteristic 0 field of, say, smooth proper things, x1, 2. It turns out you can always factorize it into finitely many stages into blow-ups and blowdowns. So at smooth centers. So there exists a factorization of the birational map into finitely many blow-ups and blowdowns. And the strong factorization would mean that you could arrange these so that it's all blow-ups and then all blowdowns. Actually, blow-ups and blowdowns at smooth centers, in fact. And this smooth center thing is a real problem if you just want to think in terms of GIT, because typically you're going to have weighted projective space things, torus singularities arising in the intermediate stages. So with GIT, you get lots of toric. It's one of the issues. Oops. But the yep. No. So that's part of the theorem. I mean, it's hard. So it's many pages. So it's not as simple as saying that the G-ample cone has only finitely many chambers. This is something more sophisticated. And I should stress again that finitely many chambers of G-ample cones actually is a simple, essentially geometric fact. Even though it follows from much more sophisticated analysis in Dlugachev and Hu, it itself is fairly direct. So it can be proven directly. All right. So what's the point here? We're saying that first of all, observe these GM actions can be used to shift within a birational class. So that's a little point to take home with you. All right. And in fact, all of GIT and the applications boil down to just, as I said, linear GM actions plus some combinatorics. And as I said over here, those are basically covering spaces. Plus combinatorics. All right, so the nice thing about covering spaces, so if you go back to your first graduate course in algebraic topology, there's this one in the book of Peter May, where he says, the theory of covering spaces is one of the few parts of algebraic topology that has probably finally reached definitive form, and it is well treated in many sources. So I think at this point, somewhat similarly, you could say that although GIT has a few additional complications, it's fairly fair to say that, a few more subtleties, it does feel like it's in a sort of similarly complete state, and even now has some nice texts, as I said, expositing it. So there aren't too many subjects in algebraic geometry that I would feel confident in saying are this complete. Notice in the background there's a sort of theory of A1 covering spaces. All right, so if you believe these analogies with topology have some merit to them, and indeed you can extract some small theorems from them, but if you would want to hopefully extend the analogies. So if you want to pursue the topological analogy further, what do we have? Well, right now we have GM actions are covering spaces. There's only a few primitive concepts in mathematics, and in particular topology. Covering spaces is one of them. But another very primitive, sometimes more primitive and even more applicable, widely applicable thing is homotopy. So you could say what goes with homotopy. Equivalences. So, well, clearly, you'd want x cross A1 to be homotopy equivalent to x. That's sort of something you would hope for. But already some interesting things begin to happen from an algebrogeometric perspective once you allow this. So let's think about what we just said there about birational geometry. What happens if instead of considering covering spaces, we allow homotopy to our birational class? Well, I mentioned a couple lectures ago that for a lot of things, crossing with A1 isn't interesting at all, in the sense that if x cross A1 is equal to y cross A1, you get back that x is equal to y. That is to say, if you have, say, positive log Kadeira dimension, for instance. So let's say this. So recall so for log Kadeira 0, that's okay. For other sort of nearly rational, very nearly rational things in some ways, it wasn't. And I gave some example of these surfaces. I gave you sort of a Q2 and a cubic. But what happens? What does this have to do with the birational case? Let's think birationally. So that there's a theorem from the 80s, a big result of Beauville, Colliot-Telen, Saint-Sucre, and Swinnerton and Dyer, which tells us that birational version of this cancellation is false. We give an explicit example of so there exists X, a smooth conic bundle. And for this, we can work over C. Smooth conic bundle over P2, such that X is not rational, but is stably rational. That is to say that X cross some, I believe it's P2, is birational to P5, but X is not birational to P3. Okay. So that's interesting. So somehow taking these homotopy equivalences can make you leave your can move you to a sort of closely related birational class between birational classes. Perhaps one that it's very difficult to distinguish normally by ordinary means, ordinary tools. So the question then is also, okay, so this is, yeah, so homotopy moves between nearby birational classes. But this is a conference about moduli spaces, and the question is also very natural with respect to the applications to moduli spaces. For instance, moduli varieties. So let's recall back from the first lecture that we had the classical question of understanding conics in the real plane with respect to the group of Euclidean motions. And you take the invariants, and yes, you pick out all of your, as you distinguish your conics as desired. Even though the group was a little bit funny, right? So you had the linear part, but then you also had your translations. These translations are unipotent, right? They're additive. They're not multiplicative. Of course, in the projective case, we didn't see this because everything's projective linear, but it's really easy to modify your problem while still being in this classical vein and to get this sort of behavior. So for example, so in projective space, the automorphism, of course, is CGLN. That's reductive. But what if we just consider instead something like a weighted projective space? Or more generally, a toric variety, or you can consider spherical varieties, or a number of other things. All right. So now, so the automorphism group is non-reductive. Let's take a quick look at an example, just to see how this sort of thing works. Take one of the simplest weighted projective spaces, P112, give it coordinates x, y, z. Then you have a copy of GL2. So look at the graded homogeneous coordinate ring and look at the automorphisms of that if you like, as a substitute for the quotienting down to the automorphisms of the space itself. But so this gives you GL2's worth from the x and y. We get a GL1 from z, and then we have to worry about their interactions. So z can also be sent to z plus alpha x squared plus beta xy plus gamma y squared. Right? Those are all degree 2 in your coordinate ring. So we have here alpha, beta, and gamma. They can be any, say, working with the complex numbers, any complex numbers. So we get that, where this is the additive group now. Right? And so if you want to, say, now study moduli of varieties as, say, hypersurfaces in the toric variety, just like we did for hypersurfaces in projective space, then you have to worry about these actions, and you have to see how that action works on a higher degree polynomial. So this is straightforward enough. I don't know, so in this case, let's say you wanted to look at something degree 4. Degree 4 would correspond to your Calabi-Yau case. So in this case, elliptic curve. All right, so hypersurfaces, which in this case are curves. It's anti-canonical, so this is Calabi-Yau. And here that forces it to be a elliptic curve. And you can go on like this for other hypersurfaces and toric varieties or complete intersections or what have you, right? So this is, I think, still people's favorite way to produce Calabi-Yau moduli. All right. Excuse me, not by quotienting like this, but by studying families of hypersurfaces in toric varieties and complete intersections. Okay, so lots of things can begin happening once you consider this sort of homotopy instead of covering space behavior. So to keep the discussion very simple, let's say x is, let's say it's normal, affine, and let's say we have g. We can have both the unipotent and the reductive part. The reductive part we kind of understand, so let's look at the unipotent part. Let's keep life easy and say it acts scheme theoretically freely. There's a few core questions that you always have to address. The first is, you know this is going to be an Artin space. So it's an algebraic space in the sense of Artin. So then you have to ask yourself, is this a scheme? This is what GIT was sort of developed to handle in a sense, right? It's, how do you force schemes? So it's either going to be a scheme or not. So we want to determine whether yes or no it's a scheme. If it is a scheme, then it's easy to see, from invariant theory if you like, that it's quasi-affine. And so the next question you have to ask yourself is it affine? And again, you'll have a yes and a no possibility. All right. And if it's not affine, then what you want to know is, does there exist, so is it in some way, does there exist a canonical embedding? So does there exist a phi into some affine closure with codimension, complement codimension greater than 1. Okay, so you want the boundary to be codimension 2 or something, and then at least up to normalization, this is just going to give you spec of the ring of invariance. Right? So this is actually Hilbert's 14th problem in disguise. Right? You need to know about finite generation of the ring of invariance. I'll give you an example in a second. Someone asked for it in the first lecture. So here, this is it a scheme question is really a stability test. In the sort of Hilbert-Mumford sense. So it can't be wrong. And it's relatively easy using this to produce counterexamples. If I had a bit more time, I'd say something about it, but I won't. So examples that are spaces but not schemes, and yet everything is smooth and as pretty as possible. You just sort of intersect with just take any old GA linear representation and intersect with a sufficiently generic high codimension subvariety. Excuse me, yeah, such that the action is free, but that's okay. So if it's, let's say, for example, just take a GA representation, look at X satisfying these conditions, so it's free action in the rep, closed subvariety of, let's say, intermediate codimension. So it's not a hypersurface, it's not super high codimension. That'll give you something with an action whose quotient is a space but not a scheme. So that's straightforward enough. So here, as I said, this is Hilbert's 14th, and this, if it is affine, then it turns out, then what you're getting is that this quotient admits a section. And in particular, things are especially simple because the G action is then conjugate to the trivial action. And so what you really have, since unipotent groups are isomorphic to affine spaces, is an isomorphism of X with its quotient crossed with some a to the k. Okay, so you need to be able to detect these. This is sort of a stability test. This test is a test of vanishing of Lie algebra cohomology. And this test, then, as I said, is a hard one. It's Hilbert's 14th problem. Someone asked for an example of a GA quotient that's going to be non-finitely generated back in the first lecture. And so let me say that. Oops. Sorry. So there are actually lots of examples. So the thing to keep in mind is we're sort of looking for quasi-affine varieties which don't admit embeddings with a codimension 2 complement, right, into another affine variety. So there's an example from an analysis paper due to Niemann, which is really classical, and Briand nicely generalized recently. But the idea is just this. You take an elliptic curve, look at the universal abelian extension, so a GA torsor on it. So we'll call this Y. Universal abelian extension. This is now something which is two-dimensional, and it's an algebraic group, so it is quasi-projective. And so it has, in particular, an ample line bundle. So all you have to do is now look at the GM torsor sitting inside that ample line bundle. So now we have a GA. We have we have an elliptic curve. We have a GA, and we have a GM. So all of our components of algebraic groups. And then this itself is going to now be a three-dimensional quasi-affine variety. And then you have to argue that it doesn't admit a codimension 2 complement, and there's a couple ways of doing it. But then the point then is that this is, so we'll call it X. The point is that K bracket X is not finitely generated. And now use take an embedding of x into x bar. So if you want to do this as a GA action, to make a GA action, one thing you can do, is take an embedding in x bar, such as this is normal. Then this is an S2 variety in the sense of Serre. So you can cut out the complement by a pair of functions. It's the zero set of f of 0 equals 0. And then you can just take the following fiber product. Okay, where the x bar goes to A2 via your F and your G, and your SL2 goes down to A2 via its invariant maps. It's just a pair of invariants corresponding to like the second row, for instance, depending which way you act with your GA for the GA action. Remember that SL2 goes down to A2 minus the origin, which is. Okay, so this is affine, it has a GA action, and everything's happy. Okay, and you recover the quotient. The quotient is your x. Okay. So there's an example of a non-finitely generated ring of invariants coming from GA. All right. So as always, basically out of time. Let me say I'm going to go 10 more minutes at most, and just say we've talked. So I said you have applications then to both moduli of bundles of varieties like hypersurfaces in weighted projective space instead of in projective space, and also to bundles. And so let's take 1 second to think about bundles in this homotypic setting. So in topology, there's a perfect theory of moduli of bundles, of bundles, or of principal G bundles. Right? So basically, if you have X as a manifold, you can identify and you let Vk of X denote the rank K isomorphism classes of rank K topological bundles, vector bundles, say. Then the basic theorem is that there's a natural bijection between this isomorphism classes of bundles and homotopy classes of maps into an infinite Grassmannian. K, I called it? K. All right, so this is homotopy classes of maps. This is the infinite Grassmannian. And of course, for principal bundles, you can do the same thing, where now you have your BG. All right, what about algebraic geometry? In algebraic geometry, we have, whereas this classical question do the same thing, but now instead of topological vector bundles, we have algebraic vector bundles. And you can ask the same thing, for instance, let's take the simplest, what might naively the simplest case, affine space. Right, so in the topological world, clearly this is trivial. It's just the trivial bundle. But in the algebra geometric world, this was very hard. Those problems of Serre solved ultimately by Quillen and independently by Suslin. And showed that indeed, it's as you would hope. You only have up to isomorphism, the trivial bundle. Right? So when X is smooth and affine, these techniques were pushed forward by Lindell to show the following. This is in canonical bijection with this. So there's some sort of homotopy invariance going on with respect to A1. So you can descend your bundles just by projection, and there's this canonical bijection. This is Lindell. So what you might hope is that this homotopy invariance extends further. And indeed, Morel showed there's a canonical bijection between the isomorphism classes, and just like in topology, you have to define what this means, of course, but just put a little A1 there. So it's now homotopy, A1 homotopy classes of maps. All right, so this is very nice. And it relies upon this, which relies upon this. Right. So to get a theory of moduli spaces for vector bundles on projective varieties, what you want to do is somehow pass to the A1 cover, namely the quasi-affine variety, or the affine cone lying over the projective variety, and then pass from the quasi-affine to something affine in much the same way that you do here with something quasi-affine to something affine here. All right? So you'd have your projective thing here. You'd pass to some affine cone above it. Or really, strictly speaking, it'll be something quasi-affine when you subtract the cone point. And then above that, you'll have something affine. And this is sort of, as I said, like an A1 cover. And this is going to be a homotopy equivalence. And this is solved by this, which reduces to this. OK, so the question is how bad are these steps? This is somewhat manageable. This step here, though, might conceivably be messy. And so I'll just write one theorem down about that. So we need to understand, so think of the intuition about what you're asking for. You want to understand how vector bundles change as you sort of twist, like here, from A2 minus the origin to SL2. I have some vector bundle down here. And I want to lift by this, pull back by the GA fibers with a little twist, and get vector bundles on here, and see if I have a pair of non-isomorphic vector bundles here becoming isomorphic here, or what happens, just what goes on. So you need to understand how the twist and pullback affects, so the twist changes the moduli. OK, so somehow the crucial point in this chart, which I maybe didn't stress, is that unlike the reductive case, so in the reductive case, I mean, somehow you have very limited singular behavior. If you have something smooth, you end up with something which is called Macaulay, or indeed just with rational singularities when you quotient. However, here, because of this boundary issue, you can get arbitrarily bad behavior, and that can be made kind of precise. So somehow there's lots and lots of flexibility with this boundary behavior, which makes the theory more flexible. And so the theorem, I'm going to state due to Arvind Schalk and myself, is that if you give me a triple of integers, n, l, and m, and let's say that n is at least 6, just for this argument, then the claim is that there exists a free, in the scheme theoretic sense, additive group action on affine space such that which yields then the isomorphism classes of vector bundles on the associated AMJ, so such that the quotient is a variety, and the associated isomorphism classes of rank k vector bundles has at least L-dimensional moduli for every sufficiently high k. And the reason I throw in this extra m is that you can actually produce m-dimensional families of pairwise non-isomorphic such satisfying this for any m. So somehow, you have to take just 1 second to think about it. What it's saying is that there's an awful lot of structure being encoded in this twist, as far as vector bundles are concerned, even though cohomology doesn't see anything. So you have this funny case. I mean, affine space, we know the vector bundles are trivial on affine space. Right? That's one system. And all we're doing is we're twisting by this one-dimensional, just this, we have this GA fiber, and it's a nice group action. You get a variety as a quotient. Everything inside separated. Everything as nice as can be. But algebraic K theory is the algebraic K theory of a point, etc. So just a simple remark is that algebraic K theory, that of a point for all of these, motivic cohomology, etc. Whatever standard cohomology theory you throw at it is kind of useless. And yet still, you get all these vector bundles. And each of these vector bundles in particular has a very trivial consequence because k naught is trivial. So in particular, each vector bundle is stably trivial. So you have tons of stably trivial. That is to say, you direct some trivial bundle, and that will be isomorphic to something trivial. So lots of stably trivial vector bundles. Yeah, so and the only thing I'll say about the remark is that this comes from, in the end, this comes from the flexibility with the boundary. And if you like, you can vary all sorts of things in the boundary. For instance, you might vary through a moduli of curves. And that gives you lots of these guys. OK, so yeah, I wanted, of course, to say a few more things, but time runs out. Basic point is that there is a nice analogy between covering spaces, topology and algebraic geometry, covering spaces we understand, homotopy theory we're in the process of understanding, and we have lots of nice little theorems en route. So if people want to chat with me about it, they can. Thank you.
Very